All right, welcome! Today, Chapter 3, Section 5.3, Unique Factorization in Polynomial Rings. And a large part of the purpose of this section is to study the interplay of the idea of irreducibility in something like z of x versus something like q of x. All right, let's start with the definition. All right, so begin with a unique factorization domain, D, a polynomial in there, f, that's not 0. We'll say that f is primitive if the greatest common divisor of all the coefficients, ak, is a unit. In other words, we can say the greatest common divisor is 1, because remember, they're only defined up to units. So you're primitive if you can't factor out something just on the basis of the coefficients, other than units. All right, in the general setting, there might be a greatest common divisor. So given f, find the greatest common divisor of the coefficients, and then factor it out. So you can write f as c times f naught. Of course, since you factored out the greatest common divisor, the coefficients in f naught won't have a greatest common divisor other than 1. And so f naught will be primitive. In any case, the definition part is that c we call the content of f, the greatest common divisor of the coefficients. And since the greatest common divisor is only determined up to multiplication by a unit, the content is likewise only unique up to multiplication by a unit. All right, first lemma. All right. Start with a unique factorization domain. Let's write f for its field of fractions. All right, part 1. For any non-zero function in f of x, field coefficients, you can find a constant in f, c, so that f is c times f naught, with f naught in d of x and primitive. Moreover, the f actually started out in d of x if and only if the c that you get this way is in d. Okay, part 2, sometimes frequently called Gauss's lemma. If you start with two polynomials in d of x, f naught, g naught, and they're both primitive, then when you multiply them, stays primitive. At first blush, this seems kind of hard to believe. Why can't you violate the no greatest common divisors? It seems like it might be hard to prove, but actually it's super easy with the right perspective. All right, part 3, again, looks surprising. If you have f naught primitive, and f naught and g are polynomials in d of x, then f naught divides g with field coefficients as possible quotients, if and only if actually f naught divides g in d of x. So the field doesn't help you out at all if you have a primitive f naught. All right, finally, part 4. Let h be a polynomial in d of x. And often we care about irreducibility in d of x, but the problem is d of x is usually way harder to understand than f of x. So this lets us shift the problem to f of x. So to detect irreducibility in d of x, it's irreducible if and only if either the degree of h is 0, so it's really a constant, and then it's an irreducible element just in the original ring D. Okay, so that's just purely D stuff. Or it's a polynomial in earnest, so degree at least 1. In that case, to be irreducible in d of x, it has to first of all be primitive, and then second of all, irreducible when viewed in f of x. So we'll have a lot more tools to attack the irreducibility in f of x, and we should be able to answer that. And primitive is kind of an easy thing to check as well. All right, so that's the theorem. Let's get to it. All right, part 1, the first statement that we had. So start with f non-zero. For that, you just you could do this in a smarter way to get sort of least common multiples, but why be more careful than you have to be? Just let D be the product of all the denominators of the coefficients of f. Once you do that, then you can factor off the 1 over d there. And you can write f as 1 over d times df, of course. But then this term here is in d of x because I killed all the denominators. Okay? Next, let C prime be the greatest common divisors of all the coefficients of df. And as we've already discussed, once you pull off that greatest common divisor of all the coefficients, you can write df as that C prime times some f naught, where f naught is in d of x, and of course it'll be primitive. And then you can just combine sort of the statements here and the statements here to get f is C prime over d times f naught. This, of course, is an f. As we've said, that's primitive, so that gives you the decomposition. So you can always do this. All right, the second statement was that f was in d of x if and only if that constant we pulled out was already in d. Now, obviously, just by looking at this baloney here, if that c was in d and the f naught was in d of x, then of course their product would be in d of x. So going this way is already done. What we want is the reverse direction. All right, for that, go ahead and write out f as it's stated. So then f is some c times f naught, where c is in the field and f naught's in d of x. Go ahead and write that field element as some a over b. Okay, and just as with fractions, if a and b have a greatest common divisor, then you can cancel those. So write a as a product of something times its greatest common divisor with b, and b is something times the greatest common divisor with a. Cancel out those greatest common divisors, and what's left will have no more greatest common divisors. All right, so that's written there. Canceling, we can assume by renaming things that the a and the b have no common factors, so their GCD is 1. All right, so we've got BF equals AF naught. Now, we're hoping, of course, to get this actually an element of D. And so what you see is that we really needed the B, that B inverse was actually already in D. And that would do it for us. In other words, we're hoping that B is actually a unit in D. So let's argue by contradiction. All right, if B were not actually a unit, then there would be some prime, so that P divided it. All right, well, remember, since P divides B, P can't divide A because we already got rid of the common divisors. Okay, well, since P isn't dividing A, since P divides this side, of course it divides this side, but because it's prime and not dividing A, it would have to divide the F naught. But P is a constant that divides F naught, and the way it does that means it divides every single coefficient of F naught, which means that F naught is not primitive, which is the contradiction. And that'll finish things up because B is now a unit, so the inverse is in D. And so this fraction, A over B, is really A times B inverse, which is in D. And so that'll do the second part of 1. Okay, let's go to number 2. For number 2, we've got two polynomials in D of x, f naught and g naught, and they're primitive. And we want to show that the product stays primitive. So that means we need to show that the coefficients have no greatest common divisor. And that means we want to show that if P is a prime, that there aren't primes dividing all the coefficients of f naught g naught. All right, so we just have to show that no prime divides all the coefficients of f naught g naught, so that the greatest common divisor can only be a unit. Okay, there's a trick to this. Let's let P be a prime here. And that is to remember that when you have a prime element, that meant the ideal it generated was prime, a prime ideal. And we had a theorem that said prime ideals, when you quotient out by them, you get integral domains. All right, so that's step one in our sort of heading towards this goal here, is that this quotient is an integral domain. Now I want to soup this up with something called a reduction map. All right, there's something we call the reduction map, and we'll study this more. It goes from d of x to d mod p, the ideal generated by p of x. It sends a polynomial f to, we usually call it f bar of x, where if you start with the polynomial f as a k x to the k, the image under the reduction map is called f bar, and it's the sum of a k viewed as an element of d mod p, x to the k. So if we were doing this mapping from z coefficients to z mod p coefficients, we're just changing all the coefficients from integers to viewing them as that same integer in that congruence class. Now it's an easy fact that I won't check here, but super easy. This is a homomorphism. All right, so now we have all the pieces in place. Let's go ahead and recap here. We have f naught and g naught primitive. So that means p does not divide all of the coefficients in either f naught or g naught. And that means, if you think about it, when you take these polynomials, to say that p doesn't divide it, it just means that you're not getting 0 here for all the coefficients. Because p divides this coefficient is the same thing as saying that you get the 0 class right here. So in particular, since p naught doesn't divide each of the coefficients of f naught, when I reduce it, there's at least one coefficient that is non-zero over here under the reduction. So primitive means that for any p, f naught, g naught, neither of these are 0 polynomials in this ring here. Now we're wanting to show that f naught, g naught is primitive. But what does that mean? That means we want to show that when we reduce it, some of those coefficients are always alive. They're not all 0. All right, so that means we want to show f naught, g naught is not 0, again in d mod p of x. But because this is a homomorphism, since it's a homomorphism, then that's just f naught bar times g naught bar. So we're done because we're in an integral domain. So that means if we start off with things non-zero, their product stays non-zero. So we're done. That's it. All right, part 3, that'll be fast. All right, we're starting off with the primitive polynomial in d of x, and it divides another polynomial in d of x, but possibly using the field coefficients. And we want to show that, in fact, we could have done the division over d of x, that we didn't actually need the field coefficients after all. All right, write g as f naught times h, where h is in f of x. All right, using number 1, we can write h as a constant with some field element times a polynomial in d of x. That's primitive. All right, combining h here with the g formula here, throwing that in, pulling the c out, we get that g is equal to c times f naught h naught. Now, the f naught and the h naught are primitive, and so we just proved that it stays primitive. But by the second part of 1, since we have g is a d of x, and this is a primitive polynomial, since g was in d of x, actually, then c had to be in d too. And then once c is in d, then because of this equation, actually, h was in d of x. All right, and that does it. So h is in d of x, which means f naught actually divides g in d of x. All right, so that leaves now only part 4 to do. So let's go ahead and turn there. All right, here we're relating irreducibility in d of x to detecting it with f of x. Now, we don't have to worry about h being 0, because that's never can be in the discussion. So for h equals to 0, let's look at the degree h equals to 0 case first. All right. In this case, clearly looking at degree, because whenever you factor something in the degrees add, the only way this something of degree 0 could be factors is with degree 0 stuff. So viewing it as a constant polynomial and asking whether it's irreducible is the same as viewing it just as a constant and asking whether it's irreducible. So there's nothing interesting going on there. Let's go ahead to the degree of h bigger than or equal to 1, because that's where things happen. All right, we want to show that h is irreducible in d of x if and only if it's primitive and irreducible in f of x. And of course, irreducible has to do with not factoring into anything except for units and associates. So we're going to sort of prove the converse of both sides here. So here's what we want to show. All right, when we switch to the converse here of both, then this will give us some traction. So here's what we want to show, that h is reducible in d of x if and only if it's the negation of the right side. So h is either not prime or h is reducible in f of x. All right, let's go to the right first. All right, so start with h reducible in d of x. So that means it can be factored in d of x as some h1, h2, where neither of those are units. Okay, so we've got this factorization. If either h1 or h2 had degree 0, then we would have a constant dividing all the coefficients of h that wasn't a unit. That means that h is not primitive, because you can factor something out of all the coefficients that's not a unit. So degree 0 for h1 or h2 gives h is not primitive. So that'll work there. All right. If the degrees of h1 and h2 are both at least 1, then this factorization is a proper factorization, meaning, degree at least 1. And means neither of these can be a unit in f of x, because we know what the units are in here. They're just all the non-zero constants. And so I have a factorization in f of x, neither of which is a unit, so it's reducible in f of x. All right, so that's to the right. Now we go to the left. All right, reverse direction. If h were not primitive, then you could factor out its content. H would be c times h naught in d of x. This, since h is not primitive, that's not a unit in d. It's obviously not an associative. And that means that h is reducible. We just factored it. All right, so that's no problem. The last case, suppose h is reducible in f of x. All right, so suppose we factored h as h1, h2, and f of x. At first, this doesn't help us in d of x because there are all sorts of fractions going on. But we can factor out those fractions in each case. So using that the first part of the lemma, c1 and c2 will be elements of the field, and f1 and f2 will be in d of x and primitive. All right, rearranging terms, h is c1, c2, f1, f2, and these guys are still primitive. So this means, all right, so we have f1, f2 dividing h and f of x, but I guess part 3 that we already did, then, because they're primitive, and the start and the finish are in d of x, then actually it divides it in d of x. So that means h is c times f1, f2, where the c is in d now. And then, because this was a violation up here of h, since h was reducible in f of x, it meant this was a proper factorization, meaning the degrees were at least 1. So the degrees are the same down here. So these are degrees at least 1, which means they're not, they're definitely not units down here either. And so that means this gives us that h is reducible. All right, so that's the end of that theorem. And we're going to use this next to show that when you have a UFD and you attach a polynomial, make it into a polynomial ring, it stays a UFD. All right, the theorem is if D is a UFD, then so is D of x. So a corollary. All right, the corollary is that if f is a field, then f of x is a UFD. And since f of x is a UFD, you can attach another indeterminate, f of xy is a UFD, and so forth. Attaching a finite number of indeterminates leaves it as a unique factorization domain. All right, let's head to the proof of the theorem. We have to prove that d of x satisfies the ACCP. So start with a chain of principal ideals, fi contained in fi plus 1, for I bigger than or equal to 0, say. And we want to show that it stabilizes. Well, containment of these types of ideals, as we said, is the same as a division problem. So that means f sub I plus 1 actually divides f sub I in d of x. All right, let's write a sub I for the leading coefficient of fi. And if you look at this here, fi plus 1 dividing fi, if you look at the two highest powers and their coefficients, the minimum requirement for this statement to be true is that the leading coefficients have to divide each other. So we get that. But this also gives us a chain of ideals in D. But since D is a UFD, this will stabilize eventually. So stabilizing means that for big I, once you get past a certain place, AI plus 1 is a unit, UI, times AI. Okay, that's just the leading coefficient. So going back to this division problem here, whatever degree f sub 1 has, only polynomials of lower or equal degree can divide it. And so these fi's either have to be the same degree, fi plus 1 will have to be the same degree as fi, or lower. And if it's lower, it's bounded by 0, so it can only drop down a finite number of times. Eventually, all the degrees of the fi's have to stabilize to one fixed degree, the last place where they drop down. All right, so this is just writing out what we said, that since the degree can only drop a finite number of times, eventually the degree of these f's has to stabilize. Okay, but now they're the same degree, and if one is dividing the other, the quotient has to be a constant. Okay, so they differ by a constant, but look you can read off what that constant is just by looking at the leading terms, the leading coefficients. Whatever the ratio of that is the same as the CI. So combining these two, we see that the fi plus 1s are the same as fi's up to a multiple of a unit, and therefore they generate the same ideal, and therefore it's stabilized. Okie dokie, so that's the ACCP, and we need one more thing to check our UFD. We have two options. We could do greatest common divisors, or we could do that irreducibility implies primeness. We're going to do irreducibility implies primeness. All right, we're going to do the constant polynomials separately. So if f has degree 0, then it's actually just a D. And we already know that D is a UFD. So therefore, it'll be prime in D. Okay, prime in D, but do we get prime in D of x? All right, let's check. Okay, suppose we have two polynomials, g and h, and d of x, and f divides their product. Okay, let's write out g as the greatest common divisor, c1 times g naught, and h as its greatest common divisor of the coefficients, c2 times h naught. So the ci's are in D, and g naught and h naught are primitive. Okay, then g times h is a couple constants in D times something that's primitive. Okay, so you have a constant times a primitive polynomial, and we have a constant, f, dividing it. And the only way that can happen is if f divides every single coefficient of this polynomial. Well, these have no common divisors other than units. So the only way f can divide this is if f divided these guys. So that tells you f divides C1 or C2, and then we're done. We get, since f is prime in D, that f divides C1 or C2. And looking back, that just means f divides G or it divides H. All right, that's the degree 0. Let's look at degree 1 and higher. All right, degree 0 is done. On to degree 1 or higher. So say f has degree at least 1 and it's irreducible. We want to show it's prime. Now we're going to actually work with the fraction field here. So let me write that. And remember, we could translate irreducibility in d of x into two statements in this case. Okay, because f is irreducible in d of x, then f is primitive in d of x, and it's irreducible when viewed as a polynomial in f of x. All right, we'll be using that. Okay, now for the irreducibility. Heading towards the primeness. Suppose f divides gh, where g and h are in d of x. We want to show that f divides either g or it divides h. All right, if it divided g, we'd be done. So suppose f doesn't divide g. In this case, our goal is to show that f divides h. Here's the trick. Okay, this is the type of thing we looked at sort of over the integers, linear combinations of the things when we were doing greatest common divisors. Now, the advantage of working in f of x here instead of d of x is that for f of x, for fields, we know that all the ideals in there are always principal. Okay? All right, so that was a theorem we proved a couple sections back. So this means this ideal is generated by a single polynomial in f of x. Okay, one thing about this ideal I is that f is in there. Okay, take p equals to 1 and q equals to 0. Since this ideal is generated by k, that means k divides f. Okay, but remember, f was irreducible in f of x. So the only way k can divide it would be that k had to be a unit or an associate. So it's either k is equal to u, where u is any non-zero thing in f, those are the units, or k is equal to u times f. All right, let's see where this leads. Well, this first case where k is equal to u, the ideal it generates is everything, because everything is a multiple of a unit. And if it's everything, in particular 1 is in there. All right, well, that means if 1 is in there, you can write it as a linear combination of the f and the g. So it's fp plus gq for some p and q, some polynomials in f. All righty, multiply by h. And then, well, obviously f divides f and f divides gh. So that says that. So we get f divides h, but this is division in f of x. And again, but f we already knew was primitive in d of x. And f and h are both in d of x. And so if you have a primitive element dividing something in f of x, it actually divided it in d of x. All right, so there we got it. So in this case, we've won. We found the division we were looking for. Let's look at the other case. All right, just as F was in this ideal I, well, G is in that ideal as well. And the ideal I was just the ideal generated by K, and in this case, K is UF. U is a unit, so we don't even have to write that there. It doesn't change anything. And in particular, this gives us F divides G, but that was specifically the case we were not doing, so that's a contradiction. In this case, doesn't happen. And so that is the end of the proof.